Today, I'll be discussing the scaling of MOS circuits. This topic is fundamental for understanding how modern electronic devices have evolved to become faster, smaller, and more efficient. Through this presentation, I'll walk you through the principles and impacts of scaling on MOS technology. My name is Arul Albert, and I'm excited to share these insights with you. Scaling refers to the process of reducing the size of features, like the length and width of components on a chip. By making these features smaller, we can fit more transistors on the same die, which improves performance because the circuits can operate faster. Additionally, smaller features mean we can produce chips more cost-effectively, as the overall fabrication cost drops. The impact of scaling is often evaluated through a few key indicators. First, we look at how much the minimum feature size can be reduced. Then, we consider the number of gates or components that can be placed on a single chip. More gates usually mean greater complexity and capability. Power dissipation is another critical factor, as smaller features can help lower the power consumed by the chip, which is essential for efficiency and heat management. Finally, maximum operational frequency, the speed at which the chip can run, is improved due to reduced distances for electrical signals, enabling faster processing speeds. All these factors together highlight why scaling is so important in semiconductor technology. Now, let's dive into the three main types of scaling models used in VLSI design. First, we have the combined voltage and dimension scaling model. Here, we introduce two key scaling factors. One for the supply voltage and gate oxide thickness, represented as 1/sigma, and another for all linear dimensions, represented as 1/alpha. Next is the constant electric field model, where alpha equals sigma, meaning both dimensions and voltage scale by the same factor to maintain a constant electric field. Lastly, there's the constant voltage scaling model, where sigma equals 1, so voltage remains unchanged while dimensions scale. Understanding these models helps us predict how device characteristics change as we shrink technology nodes. Here, we're looking at the key scaling factors for device parameters. Understanding these factors is crucial because they directly influence how a transistor performs as it gets smaller. First, the gate area plays a big role. It affects the gate capacitance per unit area, which in turn impacts the total gate capacitance. This is important because gate capacitance determines how quickly the transistor can switch on and off. Next, changes in the channel affect the channel resistance, which influences the transistor delay. Lower resistance means faster switching speeds. We also need to consider the maximum operating frequency, which is the highest speed at which the device can reliably function. Transistor current is another vital factor, as it impacts how much current flows through the device, affecting overall performance. Power-related parameters are just as important. Switching energy refers to the energy used each time the transistor switches states, which contributes to dynamic power dissipation. There's also power dissipation per gate and per unit area, both of which tell us about the efficiency and thermal characteristics. Finally, the power speed product gives us an overall measure of performance efficiency, balancing power consumption with operating speed. Grasping how these factors interplay helps us optimize device design for better speed, power efficiency, and reliability. Here, we're looking at the relationship between the gate oxide properties and capacitance in a MOS structure. We know that the capacitance per unit area, represented as C_ox, depends on the permittivity of the gate oxide material and its thickness. Essentially, the gate oxide acts like a dielectric in a capacitor, and its ability to store charge is influenced by how thick it is and the material's permittivity. Specifically, the permittivity, denoted as epsilon_ox, is a product of the relative permittivity of the oxide and the permittivity of free space. The thickness of the gate oxide is represented by D, and together, these values define the capacitance C_ox, which is crucial for determining the behavior of the transistor gate. This capacitance plays a key role in controlling the channel formation and overall device performance. Here, we are looking at the concept of the depletion width, which is represented by D. This depletion width forms around the source or the drain regions in a semiconductor device. Essentially, it is the region where mobile charge carriers are depleted, creating an area that impacts the device's electrical characteristics. The text mentions that D is scaled by AM, which refers to a certain parameter related to the depletion region around the source or drain. Understanding how this depletion width develops and varies is crucial because it influences how the device will perform, particularly in controlling current flow and the overall behavior of the transistor. This concept lays the groundwork for deeper analysis of device operation and helps explain how different factors affect transistor efficiency and switching. Here, we're focusing on a scenario where the delay is increasing in proportion to some factor. Essentially, as whatever we're measuring grows or changes, the delay doesn't just increase a little, it scales up significantly. This means the delay could have a big impact on performance or user experience, especially as the system or process becomes larger or more complex. Understanding this proportional increase helps us anticipate potential bottlenecks and plan accordingly. Here, we're looking at the concept of power consumption per gate in digital circuits, denoted as PG. This power consists of two main components: static power, which is the power consumed even when the circuit is idle, and dynamic power, which is consumed during switching activities. The static power component, represented by PP, depends on factors like the threshold voltage and supply voltage, both of which can be scaled to optimize power usage. By adjusting these voltages, we can control the leakage current and thus manage the static power more effectively. On the other hand, the dynamic power component, represented by PG, is influenced by the switching activity of the gate. This involves charging and discharging of the gate capacitances, which requires energy. The dynamic power is typically given by the product of the switching activity factor, the capacitance, the square of the supply voltage, and the operating frequency. Understanding how these two components contribute to the total power consumption is crucial for designing circuits that are both efficient and reliable, especially in modern scaled technologies where power management is a key concern. Here we see the concept of power, which is defined as the product of speed and force. Essentially, power measures how quickly work is done. When you multiply the force applied by the speed at which it is applied, you get the power output. This is a crucial principle in many fields, from physics to engineering, because it helps us understand how efficiently energy is being used to perform work. So, remember that increasing either speed or force will increase power, but the best results often come from finding the right balance between the two. Since this slide appears to be blank or does not contain any visible content, I'd like to take this moment to summarize the key ideas we've covered so far. We've discussed the main objectives, explored important concepts, and looked at practical examples to deepen our understanding. If there are any questions or points you want me to revisit before we move on, please feel free to ask now. Otherwise, I'll prepare to wrap up with our final thoughts in the next slide. It seems that this slide contains text elements that are not clearly readable or meaningful in their current form. Could you please provide more context or clarify the content? This will help me create an accurate and engaging narration for you.